Have you ever wondered why that AM radio signal you listen to suddenly seems to come in clearer from way farther away, but only at night? Or how a ham radio operator with a pretty modest setup can talk to somebody on the complete other side of the planet? Well, the answer to both those questions is the absolutely incredible physics of radio frequency propagation. For those of us in the field, this isn't just theory, right? It is the core of everything we do. Okay, let's dive into the foundational principles that make it all work. So, just to set the stage, this is part 3 of a really deep 20-part series. It's all drawn from a fantastic technical report by the pros over at RFI Detectives, who are part of Virtualization Options, LLC. Today, we're going to be building the bedrock, a really critical overview of the foundational frequency bands. So here's our game plan. We're going to start with a sort of map of the RF landscape. Then, we'll zoom in on medium and high frequency bands to really understand their unique personalities. After that, we're going to get into the why behind it all, and that means looking at wavelength. And then we'll wrap it all up with the essential takeaways you can actually put to use right away. All right, first up, the map. Look, knowing your frequency band isn't just important, it is an absolute operational necessity. It defines your tools, it defines your strategy, and honestly, it defines your chances of success. This quote from the source report just nails it. You simply cannot approach a medium frequency problem with the same mindset you'd use working in, say, SHF. The laws of physics that govern them are literally worlds apart. So the big takeaway here is that choosing your frequency, well, that's the master strategic decision that dictates the entire game. And this gives you a real sense of just how vast the RF spectrum is. I mean, the full report from RFI Detectives is incredibly comprehensive. It covers everything from 500 kilohertz all the way up to 7 gigahertz. For our explainer today, we're going to build our foundation by focusing on 2 of the most fundamental bands out there, medium and high frequency. Okay, so let's get into our first deep dive. We're starting with medium frequency, or MF. I've always loved the nickname for these signals, the ground huggers. And as you're about to see, it's a perfect, almost literal description of how they get around. So what really defines the MF band? Well, we're talking about the range between 500 kilohertz and 3 megahertz. Its signature move is something called ground wave propagation, which is what makes it such a reliable workhorse for things like AM radio and critical maritime comms. And here it is, that key detail about your AM radio. During the day, the ionosphere's D layer basically acts like a sponge, just soaking up those signals. But at night, that layer goes away, and that allows for some skywave propagation, or what we call skip. And of course, that low frequency means your antennas have to be physically enormous. So how does this ground-hugging thing actually work? It's a really beautiful piece of physics. You see, the wave isn't just traveling over the ground. It's practically making the ground a part of its engine. It literally induces currents in the Earth's surface, and these currents re-radiate energy that continuously pushes that wave forward. That's what lets an MF signal actually bend with the planet and travel way beyond the line of sight. But here's where it gets real for us as engineers. The performance of that ground wave is completely at the mercy of ground conductivity. Seawater, it's a near-perfect conductor, which is exactly why MF is so vital for maritime use. The signals can travel for incredible distances, but try to send that same signal over a dry, rocky desert, the range just collapses. It's also super important to remember that as you climb in frequency towards that 3 megahertz mark, the ground wave range shrinks fast. And the terrain itself, it becomes part of your circuit. A river valley can act like a waveguide, but a mountain ridge can be a total brick wall. Okay, now let's climb the spectrum a bit to high frequency, or HF. If MF signals are those dependable ground huggers, then HF signals, they're the adventurous globetrotters. This is the band that connects continents, and it uses a completely different and way more dramatic method to do it. Now we're in the 3 to 30 megahertz neighborhood, and the name of the game here is skywave propagation. This is the magic behind ham radio, shortwave broadcasts, and pretty much any application that needs to span an ocean. But here's the most important thing you need to remember about HF. It is wildly variable. This is not a set-it-and-forget-it kind of technology. It's a living, breathing system that's dictated by the sun, the time of day, and the season. And this slide right here brilliantly shows how that transoceanic journey happens. Instead of clinging to the ground, an HF signal is aimed up at the sky. It travels up until it hits the ionosphere's F layer, which acts like a giant mirror in the sky. It bends or refracts the signal right back down to a distant point on Earth. It's this incredible celestial bank shot that allows a pretty low-power signal to just hopscotch its way around the world.
So we've seen what happens with MF and HF waves, right? One hugs the ground, one bounces off the sky. But the really fascinating question is, why? Why do they behave in such fundamentally different ways? Well, the answer comes down to a single, powerful physical property: wavelength. It's the master key that unlocks all the secrets of RF propagation.
And there it is, lambda equals c over f. Wavelength is simply the speed of light divided by frequency. Now, it looks deceptively simple on the slide, but this inverse relationship is the root cause of every single complex propagation behavior we see out in the field. As your frequency goes up, your wavelength goes down. And that single fact changes absolutely everything about how that wave interacts with the physical world. This slide right here just makes the physics of it all so tangible. Think about it. At 500 kilohertz in the MF band, your wavelength is a whopping 600 meters long. A single wave is longer than 5 football fields. At that kind of scale, an entire hill is a relevant object for that wave to interact with. Now let's jump way, way up to 5 gigahertz. Your wavelength is now just 6 centimeters. Suddenly, an object as small as a single raindrop becomes a significant obstacle that can scatter your signal. This staggering difference in scale dictates everything, from the size of your antenna to the type of foliage that can block your path. Okay, so we've covered the map, the very different modes of MF and HF, and the core physics that drives them. Let's bring it all home now and distill this down into the kind of actionable intelligence you need in your day-to-day work. So there are 3 key things to lock in here. First, always match your frequency band to your mission objective. If you need rock-solid, predictable local coverage, you should be thinking MF ground wave. If you need to cross an ocean, then you've got an HF skywave challenge on your hands. Second, you have to account for the environment as an active part of your system. For MF, that means obsessing over ground conductivity maps. For HF, it means understanding and predicting the behavior of the ionosphere. And third, and this is a big one, never, ever forget about scale. Wavelength is the ultimate deciding factor for every piece of hardware you design and every single signal path you troubleshoot.
And I want to leave you with this final thought from the report because it really captures the art and science of our profession so perfectly. We aren't just manipulating electrons in a circuit. We are in a constant dance with a vast, dynamic, and powerful natural system. Our job is to understand its rhythms, respect its power, and engineer our solutions to work in harmony with it. And that, right there, is a fascinating challenge we're going to continue to explore in the rest of this series.